Barta, where we invite academics and professionals to deliver their talks. Our guest for today's talk is Dr. Dootika Vats. Dr. Dootika Vats is an assistant professor in the Department of Mathematics and Statistics at IIT Kanpur. Previously, she was NSF postdoctoral fellow with Professor Gareth Roberts at the University of Warwick. She obtained her PhD from University of Minnesota Twin Cities, working with Professor Gillian Jones. Her research interests are Markov chain, Monte Carlo, output analysis for stochastic simulation, and stochastic optimization algorithms. Today, she will speak about efficient Bernoulli factory MCMC for intractable posteriors. Um, we welcome you, Dr. Watts. Without further ado, I invite her to take the virtual stage and begin her presentation. Over to you.
Thank you, Rucha, and thank you for inviting me. Like I said before, I invite everybody to ask questions in the middle. I recognize that the topic might be slightly more alien than some of the other seminars, maybe. If it is not, it's great news for me. But if it is, then feel free to unmute and ask in the middle because I will not be able to really see the questions in the chat box. Or so don't be shy, just shout at me and I will stop in the middle, right? Okay, so I'm going to talk about efficient Bernoulli factory MCMC for intractable posteriors. The way the slides are designed is I will talk a little bit about intractable posteriors. I will talk a little bit about MCMC. I will talk a little bit about Bernoulli factories, and then I will spend a reasonable amount of time talking about efficiency. Um, so I realize immediately for the intended audience, I've not written the word Bayesian anywhere, and that word is important. So the premise, if you're coming from the sort of machine learning literature, is that we are looking at Bayesian models. Okay, that's the premise. We're looking at Bayesian models. So we consider a Bayesian model for parameter estimation in the sense that we have a particular theta that is a parameter that characterizes some information about a modeling strategy, and we have observed data y, uh, and we assume some likelihood function or loss function, as if you might recognize in that way, a likelihood or loss function that measures the sort of effectiveness of data given a particular value of the parameter. And then because we are going to be in a Bayesian setting, we are assuming prior information on the particular theta or the parameter of interest because we're coming from a place where we think we already know something about the problem. And then having observed the data through a half of the Bayes rule, we can get a posterior distribution, the density for which I denote by pi theta given y. And that I'm going to denote as proportional to pi tilde theta given y. The idea being that in any realistic problem, the proportionality constant that makes this pi tilde a valid density, that constant is typically unknown, and you can't really find it out, and that's one of the reasons why it's intractable. So like I said, so the posterior is often complicated enough that that is only known up to this pi tilde. And because of this reason and other reasons, often a way to actually understand something about this posterior distribution that has all of our information gathered from the data and our model, is to use something called Markov chain Monte Carlo algorithms or MCMC algorithms. And what these algorithms, MCMC does, is it goes to your posterior distribution and says, okay, I don't really know what this looks like, but what I can do is I can get samples from this distribution, and then I can guess things about the distribution using these samples. Okay, so the goal in MCMC is to draw samples from a potentially intractable distribution. These samples are not going to be nice samples, they're going to be correlated samples, but samples nonetheless. Right? Any typical MCMC algorithm or a lot of MCMC algorithms belong to the following premise and work in the following way. That what they do is they start with a given point, a given draw, and you can start with a fixed draw, or you can start with any draw in your parameter space. So you start with some theta star, and then the k plus 1th update, you start with some theta 0 or theta 1, and then the k plus 1th update of this Markov chain that is going to lead us samples from this target distribution goes in the following way, that you generate a theta star from some Q. Now this Q is your proposal distribution that depends on your previous draw, or potentially depends on your previous draw. So based on where we were before in my draw, I draw a proposal Q star, and then I tell my algorithm, hey, is this a good draw? Should I accept it? So if it is a good draw, then it will be accepted as the next draw theta k plus 1 with some probability alpha that depends on where I was before theta k and where I have proposed to go. Okay. If it is not a good draw in that regard, that it is rejected at this point, then our next draw, theta k plus 1, is the same draw as theta k, which means that I am going to hop where I am. In this way, what we do is we run a Markov chain, because this process, because I get a theta k plus 1 conditional on theta k, it runs a Markov chain. And this Markov chain has, using all the literature from stochastic processes, has things about being a stationary distribution and a limiting distribution and sort of periodicity and recurrence and so on. We can study these Markov chains and have them help us in getting samples from our target distribution, which is a Bayesian posterior. Obviously, in this whole process of steps 1, 2, and 3, nowhere does the actual posterior seem to come in. And it is actually hidden in this alpha. So the probability with which we are going to accept or reject a draw is chosen so that it actually involves our posterior distribution and keeps the posterior distribution invariant or stationary for this Markov chain. What that means is that if I run this algorithm steps 1, 2, 3 with particular choices of alpha, which I will talk about, then eventually I will get draws from my posterior distribution. This is the premise of an MCMC algorithm. Now, the thing is, if this alpha acceptance probability can be evaluated, we can actually calculate it, then obtaining an event with probability alpha, so actually implementing step 2 on a computer, is straightforward, because what you do is you get a uniform coin, uniform between 0, 1, and check whether u is less than equal to alpha or not. This uniform less than equal to alpha happens with probability alpha. So this becomes an alpha event, and then we can implement step 2 of the algorithm from a computational perspective. But obviously that this assumes that we can actually evaluate alpha, right? And why am I talking about evaluating alpha? You'll understand in the next slide. A popular acceptance probability that is used is the Metropolis-Hastings acceptance probability. So there are multiple choices of alpha that could be available to us, but the really most popular one is the Metropolis-Hastings alpha, which leads to the very popular Metropolis-Hastings algorithm. If you've seen Oppenheimer, then Teller was one of the characters in Oppenheimer, and Teller was one of the co-authors on the paper the original Metropolis Hastings paper. So the authors of the paper are Metropolis Hastings, Teller, and Rosenbluth. So Teller makes an appearance in Oppenheimer as well. So alpha MH, the acceptance probability is the minimum of 1, pi, the posterior distribution evaluated at the proposed value, divided by pi, the posterior density evaluated at theta, which is theta k, times the ratio of the proposal densities switched in the conditional. So theta given theta star in the numerator and theta star given theta in the denominator. Now there's a reason and proof as to why this particular acceptance probability works. I'll not really talk about that, but I'm happy to share resources. But the important thing to note here is that recall that pi we could not actually write down because it's only known up to a proportionality constant. But that's not an issue, because whatever is the constant in the numerator is a constant in the denominator, and that cancels out. So I can just write this as pi tilde and pi tilde, which means I can actually evaluate this alpha, right? So because I can evaluate alpha, then MH can be implemented easily for any target density pi that I can evaluate, right? It may be a posterior density, it may not be a posterior density. However, there are something called doubly intractable posteriors or further intractable posteriors, which might look at the following form. We might get target distributions or posterior distributions that actually cannot be evaluated even up to proportionality. For example, for some reason, we may arise at posterior distributions pi theta given y in such a way that they take the form of an integral of some function g of theta and eta given y, where I'm integrating out some nuisance parameter eta. So eta is a parameter I'm not interested in. I'm integrating that out, and I just get integral over eta g theta comma eta given y. This happens often in certainly happens a lot in problems where there are priors on constraint spaces. So if you're trying to fit a model where the parameter space is in a very complex constraint space, we'll see an example of this one at the end. It happens when there's missing data and we're imputing missing data, and it happens very often in Bayesian inference for diffusion processes. And here to
There
give this,
is,
yeah.
yes, so there is a question. Another, you want to unmute?
Hello, Dr. Vats.
Yeah, hi, another.
So I wanted to know, like, so here you said that it is intractable. I wanted to know, like, what would be the prior and the likelihood here?
So, okay, so I have not described it in that sense over here, but if I go back a few slides, so I'm going to go back to the first slide. So you can think of it in the following form. So I still have this particular setup and that this holds true. But now imagine if the prior is in the form of an integral that I can't calculate, or the likelihood is in the form of an integral I can't calculate. Right? So the likelihood is in the form of an integral, or the prior is in the form of an integral, then the whole posterior becomes in the form of an integral. Right? Does that make sense?
So what was the G there?
So now G I have defined as any generic function which denotes the product of f and pi multiplied such that it is inside the integral, right? So I'm saying
So
the G.
we can sample from the G, right?
Say that again.
So given some samples from the data set, we can calculate that Z.
Yes. So so one argument is that we can actually sample from this over here, but this may not actually define. So you notice that this may not actually define a valid density. Now, if it does not define a valid density, we can certainly normalize it. But then the normalizing constant is a function of theta and eta, potentially, right? Because we're integrating out eta, so it could be a function of theta, and then we don't know that.
Okay, so
Does that make
theta
sense?
is one extra variable that we have,
Yeah,
something that
yeah,
we don't know.
yeah, exactly. Yeah. We'll see. We'll see. I've presented it a little abstractly, so you'll see exactly how these things arise in the example towards the end, unfortunately. But if it's possible, just buy into the premise that this is this is a situation that arises, and a solution needs to be obtained. Okay.
So I'm just asking that we can't do a Monte Carlo here to estimate this integral.
Okay. So yes, sometimes you can do a Monte Carlo, but then those are approximations, right? So you may not get theoretical guarantees. So what is going to happen is, for if you want to do a Monte Carlo approximation as a function of theta, so on the left hand side we have this as a function of theta. We can do a Monte Carlo approximation, let's say, and we get the right hand side approximation as for a given value of theta, we can get a Monte Carlo approximation. But now I want to sample from pi theta given y, right? So now I need the whole path or the whole Monte Carlo evaluation for every single given value of theta, which typically theta is in some general state space,
Okay.
right?
Okay,
So
now it
if
is clear.
yeah, so if we allow ourselves to do sort of a series of approximations and get some crude answers, that's certainly possible. But if we want to be statistically valid, then that becomes challenging. Okay. Okay.
Okay, thank you.
Mhm. Thank you. Thanks for the question. Okay, so but if this is our premise that this is the pi, the density we are interested in sampling from, and this is the best, this is an example of how it may be available to us in the form of an integral, then now I can no longer evaluate alpha mh, right? Because now alpha mh is in the form of an integral. In every step, yes, Anada's question was correct that we can every step approximate that integral and get an approximation of alpha MH, but it is still an approximation and not theoretically valid. And those approximation errors can lead to a butterfly effect of invalid inference at the end. So we want to make sure we're doing it in a holistically correct, mathematically correct way. So currently we're not open to doing those approximations. Okay, so alpha MH cannot be evaluated is the takeaway message. So let's look at some other alphas. Another alpha is the Barker's alpha coming from a paper in 1965. And the Barker's acceptance function is pi theta star given y, q theta given theta star, divided by the same the same times pi theta given y times q theta star given theta. It involves the same exact components as alpha MH, just in a different ratio. And this alpha b is automatically between 0 and 1. So it's automatically a probability, which means we don't need a min function to make those corrections. Now, Barker's acceptance function is actually not popular at all. And that is because of a very popular result that was due to Peskin in 1973, which is called the Peskin's ordering result, which basically stated that, and I'll show that in the next slide, but basically it says that alpha b is always smaller than alpha MH. For any two given theta and theta star, alpha b is always bounded by alpha MH, which means we're always accepting with lower probability, which means we never want to do that. We always want to accept with a higher probability. We always want to go to alpha MH. So Peskin's ordering basically says that using Metropolis Hastings acceptance is always going to be more efficient, statistically speaking, than Barker. How do we show it? How does Peskin show it mathematically? Well, consider the sequence of x's, or here, I apologize, x means any path of a Markov chain. So these x's now denote my theta k's. And I take any Monte Carlo average of those Markov chain paths. So I take an average of those Markov chains. And let's say I take average of the Markov chains coming from PB, which is Barker's kernel, and PMH, which is the Metropolis Hastings kernel, right? So PB denotes Barker's acceptance function, and PMH denotes Metropolis Hastings acceptance function. Then basically, if var P comma H basically denotes the asymptotic variance of these Monte Carlo averages, what is the quality, which represents what is the quality of my Monte Carlo average when I have infinite samples, then the variance arising from MH, Metropolis Hastings, will always be less than equal to the variance arising from Barker's. So this other side, this left-hand side of the inequality, series of inequalities, is the reason why Barker's was immediately dropped when Peskin's result came out, and PMH is universally the one acceptance probability that's always utilized. But on the other hand, more recently, and somewhat hinted in the original Peskin paper, there's also an upper bound that says, okay, PB or Barker's is not as good, but it's not as bad either, because the variance is actually upper bounded by 2 times the variance of MH plus the target variance of the function involved, which this one is typically much smaller than this variance. So it's basically bounded above by 2 times the variance of Metropolis Hastings. So although Barker's is certainly more statistically inefficient, it is not too much so. But there's no reason for us to use Barker's if MH can work, is basically the takeaway, which is why people haven't used the Barker's acceptance probability, or in fact, any other acceptance probability. But in this talk, I'm going to focus on the Barker's acceptance function. But I'm still faced with the same problem that even if I want to use the Barker's acceptance function, it doesn't solve the issue. Because remember, I'm dealing with doubly intractable posteriors, which take the form of an integral. And I can still I still cannot evaluate alpha b. This alpha b still has these integrals in the ratio, and I can't evaluate it. Okay. So what do I do? And a solution to this is what is called the Bernoulli factory. Now, if we trace the origins of what a Bernoulli factory is, we go into a series of what arises in the CS literature. There's not a lot of literature on Bernoulli factories. I'm not sure exactly why. I don't think it's a very interesting area for most people. but it can be really useful in some simulation problem spaces. So I'll explain what a Bernoulli factory is. It's quite simple, actually. So here's what a Bernoulli factory is. A Bernoulli factory is an algorithm that generates Bernoulli events of probability HP for some function h using only Bernoulli p events. So think of it this way. Very simply, let's say you have one fair coin, not fair coin, a biased coin that comes up with heads with probability p. Let's say I ask you to give me a method of simulating a Bernoulli coin of p cubed probability. Okay, so your h function is h of p equals p cubed. Given infinite resources, infinite number of coins of Bernoulli p, you want to get one event of Bernoulli p cubed. Then the way to do this is to get 3 coins. You have infinite coins, but you get 3 coins and you toss them consecutively. If all 3 of them comes up heads, then because these are 3 independent coins, they'll come up heads all 3 together with probability p cubed. Okay? So your Bernoulli factory works in the following way. It goes and gets 3 coins, and if all 3 of them are heads, it says success, otherwise it says failure. That's a Bernoulli factory. Okay. Of course, this polynomials of such kind are very simple. There's a rich literature on what kind of functions are good, what kinds of functions are not good. But what we are going to do is we are going to want events of probability alpha b without evaluating it. Okay. So what I'm going to do is I'm going to basically map h of p to be alpha b, and without evaluating alpha b, what can I use to actually get events of probability alpha b? That is going to require a Bernoulli factory. Okay. This work, I should have mentioned in the beginning, is joint with Flavio Gonçalves, who's at UPMG in Brazil, and along with Krzysztof Laczynski and Gareth Roberts at Warwick. And so in a paper in 2017, the 3 of them proposed the following, where they said, well, let's suppose there is a C theta, which upper bounds my pi times my q. Okay, so this pi times q is what comes up in the numerator or denominator of my alpha b. So let's suppose, it's a weird assumption, but let's suppose that pi and q can be upper bounded by c theta. If it can be upper bounded by c theta, then I can write pi times q as some c theta times p theta, where this p theta is just the remaining term after the upper bound. So p theta is nothing but pi times q divided by c theta. This number being guaranteed now to be less than equal to 1. I have now successfully decomposed pi times q as c theta times p theta, where p theta is now is a probability because it is between 0 and 1. So if I have this set up, then I can do the following. So I'm going to assume I have this set up. I can then rewrite alpha b, which takes this particular form over here, this particular ratio, as just c theta star p theta star divided by c theta p theta plus c theta star p theta star. So I've just rewritten the numerator as cp and the denominators as cp. Using this framework and the fact that this c is some known bound and the p's are some probability, they propose what is called the 2-coin Bernoulli factory algorithm. So what is the 2-coin Bernoulli factory algorithm? It says, okay, let's draw one coin, C1, that gives success with probability C theta star divided by C theta plus C theta star. If this first coin, now I know these completely, the C's I know, so I can evaluate this easily. If this first coin is 1, then I draw a second coin that is Bernoulli P theta star. Now, I don't know P theta star because remember, I have decomposed pi and q as C theta P theta. And pi I don't know. So if I'm assuming I know C, then I don't know P, right? Which we'll get to in a bit. So, but somehow, if I can draw C2 Bernoulli P theta star, then if C2 is equal to 1, then I output 1. Output 1 meaning accept my proposed draw in my accept reject algorithm. If C2 is 0, if this second coin is 0, then I go back to step number 1, which is this step over here. Now, if the first coin was 0, then I draw a second coin, which is Bernoulli P theta, where theta is my current step. And if the second coin is 1, then I output 0, which means reject the proposed coin. And if C2 is 0, then I go back to step number 1. And it's fairly easy to show that this above algorithm will output 1 with probability alpha b, which is the Barker's acceptance probability. So the above algorithm will output 1 with this particular probability. The question though is, I don't know p theta, so how can I actually sample Bernoulli p theta? I can hear a ping, so maybe there's a question. Yeah.
Yes. So if C2, so 2.1, I'm looking at 2.1. So C2 is done sampled from Bernoulli P theta star.
Yes.
Now, when should I make the jump? Like when should I accept it?
Sorry?
When should I accept the proposed solution?
Yeah. So if this C2 turns out to be 1, then output 1 means accept the proposed step.
And if it is 0, then we don't. So then
if it is if it is 0, it's not that we don't accept it. If it's 0, then I go back to at the beginning of the Bernoulli factory. So for that same theta, C theta, and the same C theta star, okay, I restart this process again.
So I'm really confused. Like, how does this work? Why is it that it is equal to alpha b?
Okay, so the proof will take a little bit of an effort, so I don't want to go into the proof necessarily, because let me see if I can intuitively explain it. So what I'm trying to do is I am trying to so let's understand it this way. What happens in steps 2.3 and 3.3 is that the algorithm loops again. Okay, so it keeps looping until it's ready to give you an answer, whether it's 1 or 0. Okay, now it will give 0 if C1, the first coin, turns out to be 0, as in this C theta is much larger, right? Which means that this ratio is smaller. Then it's forced to go to this C1 equals 0 step. And then if P theta is larger, then it will go to C2 equals 1 and then output 0. Okay. I don't want to get into the proof necessarily right now. What you basically have to do is have to understand the recursive loop that it gets into, and then you sort of just see that this turns out to be alpha b.
Okay. So
it's not very satisfying.
You could be stuck in a loop for a long time.
Exactly. That's it. So the point I'm going to eventually make is this looping is the problem.
Okay.
Let me just take a second to highlight what's really. Let's take a second to look at the big picture once. Sorry. So what I'm basically done so far is I have step 1. Step 1 I'm not changing. Step 3 I'm not changing. Step 2 I am not changing. What I'm doing is I'm changing this step over here. Right? So this thing where I say get uniform from U01 and check whether U is less than equal to alpha or not, this I cannot do because I can't evaluate alpha. So what I'm doing is I'm somehow coming up with another way of implementing step 2 without actually evaluating alpha. So the actual Markov chain I am not changing, really. What I'm only doing is coming up with another way to implement this step with probability alpha. Okay, and in order to do that, in order to get this with probability alpha b denoting Barker's acceptance, I will need to run that 2-coin algorithm Bernoulli factory in this recursive way until it is ready to give me some output, either 1 or 0. Right? Is this good, Ananda?
Yes.
Okay.
Yeah, that I understand. So, but we have already established that Barta is worse than Metropolis Hastings.
Yeah. So again, I will hopefully answer all of these questions. Okay. Yeah. So let me say this: that it is. I forgot to put the reference here, but it has been proven that there is no Bernoulli factory for the Metropolis Hastings acceptance function. Okay. So that means that if I know Metropolis Hastings is supreme, but there's no Bernoulli factory possible. So then my hopes are gone there. right? But what I know is that Barker's is not as good, but it was also not that bad. So if I can implement Barker's or something similar to that, then I could do something when I couldn't do anything before.
Okay.
Okay.
Okay. Yeah.
Uh, uh, could you explain, Shubhankar, what you mean by you would still get a guarantee, which is not possible?
I think you still would have some bounds available if you go with Barker's, right?
Yeah. So exactly. So
Yeah.
you have this particular mm, yeah, this the upper bound over here at least ensures that it is not infinitely worse,
Yeah.
right? That it's actually fairly reasonable if we can just get it to if we can implement it. It's at worst it is twice as bad. That's it.
Yeah. Yeah. Some guarantee is better than no guarantee. Yes.
Exactly. That's exactly right. That's exactly right. So that's the idea that they started with. Um, Now the question is that I've set this up, but obviously this step seems difficult. How do you get the C2 coin? And C2 coin is then obtained exactly in the way Anada had proposed, is using a Monte Carlo approximation. So what we do in the C2 coin, or what they did in the C2 coin, is we note that P theta takes this particular form of pi times q divided by C theta. But now recall that pi, my target density, it basically is of the form is of the form integral of g theta comma eta given by d eta. Right? So I've just substituted the assumption I had about pi. Pi was taking the form of this integral. Now, although the following is not necessary, but let's just for the sake assume that this integral is defined on some bounded space. This is not a necessary assumption. We can easily get rid of this. But if it is defined in the bounded space, then I can do a simple Monte Carlo type approximation where I can do the following. I can draw n, a random variable n, from uniform within the support of eta. So uniform within the integral bounds of eta, right? And then I can just say set m theta to be q times g evaluated at n. Sorry, I think this theta star is a typo. This should be theta, not theta star. I can just, instead of eta, I just replace that eta with my Monte Carlo sample n. And this m theta, if I just calculate the integral of what is the expectation of m theta, that is just p theta. Okay. So if I do this method of doing something naive, just getting a random draw from the finite support or uniformly from the finite support, just plug it in G, that's some estimate of this whole ratio. That estimate M theta has expectation P theta. So now if I draw my C2 coin with Bernoulli M theta instead of P theta, Bernoulli M theta, then the marginal probability that C2 is equal to 1 is nothing but the expectation of the indicator that C2 is equal to 1, where then I can use iterative expectation to show that this is the expectation of the indicator given m theta. Now, given m theta, this is the probability that C2 is equal to 1, and that turns out to be p theta. Okay, which means that given m theta, if I draw C2 from Bernoulli m theta, then marginally that is C2 from Bernoulli p theta. Okay. So that means that if I draw this capital N uniform and then ignore this capital N, don't really think about it, then I get a draw from Bernoulli p theta, which is really what I think in the Monte Carlo approximation, which Anada was referring to in the beginning, this is really what we're doing. It's a very bad Monte Carlo approximation because it's only one sample. But we don't need 10, 50 Monte Carlo steps here. All we need is one, because the only thing we're using is the unbiasedness here. Okay, if once we do this, then we can put this back in the algorithm, and now steps 2.1 and 3.1 can be implemented using this sort of Monte Carlo trick. But what happens in this two-coin algorithm is that the algorithm restarts if p theta or p theta star are small, right? So if this step or both are small, then repeatedly it will go to 2.3 or 3.3, and repeatedly it will go back to step 1, and repeatedly it'll start getting stuck in a loop. Okay. So what happens is that realistically, when we try to implement this, and this is what the authors saw when they came up with this, that it can work when you choose your proposal distribution well. But if we start proposing unlikely values that are very far away from our mass in the posterior distribution, then doing one step of the Markov chain leads you to be in almost what seems like an infinite loop of just the Bernoulli factory. So it's not able to decide whether to accept or reject this draw because it is stuck in some infinite loop. Okay, this is really the problem that we were facing when in that particular, as a consequence of this particular work. It's a really cute and nice idea, but sometimes it would not work practically because of this issue, often actually. And so our solution to this is what we call the Portkey-Barker's algorithm. What we notice is that now that pi is not available to us up to proportionality in this particular problem, it is available to us in the form of an integral. Our acceptance probability now no longer needs to be a ratio of the target densities, because as it is, whatever constants need to get cancelled may or may not be cancelled. We have a bigger problem that there's an integral, right? So we no longer need the acceptance probability to be a ratio of the target densities. And once we open ourselves away from that particular restriction, we can potentially do other things, which leads us to the following Portkey-Barker's acceptance function, which for some function d of both the proposed value and the current value, I define alpha p, which is p stands for Portkey, to be the same as Barker's, but there is an extra d term that's added in the denominator. Okay, this d term that's added in the denominator, if I assume that is symmetric, then alpha p, this acceptance probability, yields a pi invariant Markov chain. Okay, which means that my Markov chain will target the correct posterior distribution as long as d is symmetric. So d, I can switch theta and theta star, and that doesn't change d. Okay, what the actual d we consider is of a little weird form. It is 1 minus beta by beta times c theta star plus c theta, where these c's are the same as the bounds on pi and q that we obtained before. What I note immediately is that if I plug beta equal to 1, then this whole added term will get cancelled and I get back the Barker's acceptance function. Okay? So this, for any given value of beta, this is denoted as alpha beta. Okay, there's lots of notations now floating around. Okay, so how does this help? Where are we actually going with this? Why are we doing this? We'll get to in a second. But what I have to recognize also is that ideally I want to choose beta very close to 1 so as to remain close to the Barker's algorithm. See, what's happened is we have alpha mh, which is then greater than equal to alpha b, the Barker's algorithm. But now I've added some positive constant in the denominator, which makes it even smaller. So now alpha beta is even less than alpha Barker's. Okay? So I want this beta to be as close to 1 as possible so that I'm as close to Barker's as possible. That's really it. And this is really this logic, intuitive logic, is converted to the following result, where I said for beta greater than alpha, we showed that the variance of the Monte Carlo estimators from let me move one slide back. Okay. From Barker's is upper bounded by beta times the variance of the alpha beta function times again a small factor, which we're not going to get into. Okay, so that means that PB is bounded above by some smaller number than variance P beta. This doesn't really give us the right inequality, and it's a little difficult to go in get a variance bounding on the other direction without further assumptions. So the assumption that we then make is that if there exists gamma greater than 0, such that both P theta star and P theta are more than gamma, right, universally, then the variance in this Portkey beta algorithm is upper bounded by some fraction that is larger than 1 times variance of P Barker's. Again, still doesn't give us something very good, because there's no way we're going to get a variance that is better than Barker's, right? So again, going back to some very pointed and great questions Ananda has asked so far, is that then why use portkey Barkers? Because nothing's really working in our favor. We're getting some sort of results as to it's not infinitely worse, but that's about it. And the reason is the following, is what I can do is I can come up with a Bernoulli factory for this acceptance function that can make it much, much more efficient. So the Bernoulli factory I show here is the same as before, except 3 steps added in the beginning. The 3 steps is through what is the portkey coin S. So we draw a portkey coin S, which is Bernoulli beta, which means if beta is large, S is typically going to be equal to 1. So if beta is close to 1, then I set S equal to 1, and S equal to 1 runs the usual Bernoulli factory algorithm, the 2-coin algorithm. But when S is equal to 0, then I output 0 without even looking at anything. So if S is equal to 0, then I immediately reject. And if S is equal to 1, I run my 2-coin algorithm. But whenever the 2-coin algorithm used to loop, it no longer loops back to 3.1, it loops back to step 1, which means I then have the luxury of potentially going into step 2 and rejecting in the next loop. And if I set beta to be not insanely close to 1, but like 0.90 or 0.99, then if it's 0.99, then on average, 1 out of 100 loops I will reject, which is much faster than what I would have seen otherwise. So this S coin is called the portkey coin. If you're familiar with Harry Potter, what it allows you to do is it allows you to escape from a tough situation, right? If you're in this infinite loop, which is a tough situation, it allows you to escape out of that tough situation. Okay. Yeah.
So if this beta is like very close to 1, or if it is 1, then it becomes the Barker's algorithm.
Exactly.
And with some probability, we are saying that we will reject Barker and we will just reject like the next candidate, whatever.
Exactly. But so very close to 1, let's say a number very close to 1 is, for example, 0.99, right? We think it's very close to 1. It depends on our definition of very close, but seems very close to 1. Now, 0.99 means that on average, 1 out of 100 draws from this Bernoulli will be a rejection. Now, that means that on average, 1 out of 100 times, the loop will definitely break 1 out of 100 times on average. So we are artificially, probabilistically limiting the infinite length of the loop that could have happened before. We're almost putting a probabilistic upper bound on how many loops is the algorithm going to take.
Okay, so we're trying to make sure that like we need an average of 100 steps before we reject it.
Yeah, if it was going to be rejected to begin with, if it was going to be in an infinite loop, then there's an upper bound of 100 steps. It's possible that it would not get into big loops, in which case it would very quickly give me an output on lines 3.22 and 3.32, in which case, the S coin is not useful. It doesn't change anything. So if the original portkey does not get stuck in large loops, original 2-coin does not get stuck in large loops, nothing really changes, really. But if it gets stuck in large loops, then when it's getting stuck in these large loops, there will come a point where S will be equal to 0 and will escape out of those large loops.
So can I just see the previous slide once again?
Yeah, sure.
So we have the freedom to choose beta here, right?
We have the freedom to choose beta here, correct. Exactly. This is our tuning parameter. We can choose it to be whatever we want.
And this 1 minus beta divided by beta times c is theta star plus c theta. That is, you said it was some d something.
Yeah, so this is a symmetric function in theta and theta star, right? So basically, first what we did is we created a class of acceptance probabilities where if you add any symmetric function like theta minus theta star whole square, that is also going to be a valid acceptance function. Okay, but the particular choice of acceptance function we choose is 1 minus beta by beta times c theta star plus c theta, because our portkey 2-coin algorithm returns 1 with this probability.
Okay. So we are trying to make sure that. Okay. I understand because of the symmetricity. Okay. Thank you.
Because of the symmetricity, exactly.
Yes.
Yeah. Okay, good. Okay, so sorry. This particular algorithm, the Portkey two-coin algorithm, returns one with probability alpha beta that was just shown just now. And so that means now we have a Portkey, a Bernoulli factory algorithm that can be put in that step 2 of my 3-step Markov chain that I want to use to simulate from a distribution. One quick note is we can also do something called flipped Portkey. If we divide my general acceptance function, which is this alpha p acceptance function, throughout in the numerator and denominator by all of the elements involved, so pi theta star, q theta given theta star, pi theta, and q theta given theta star, then this ratio will look like this ratio, where I have pi theta given y, pi theta star given theta inverse, and similarly in the denominator. And this d will become some d prime, which is still a symmetric function, because what I'm dividing by is a symmetric function of theta and theta star. If I do this, then what now I notice that now everything remains the same, except the object in the numerator and denominators look slightly different. But now what I note is that now if I can, instead of upper bounding pi and q, if I can lower bound pi and q, then I have an upper bound for the inverse of pi and q, which means that then I can use Portkey two-coin algorithm again over here, because there is straight equality for going from here to here to here. So now instead of upper bound C, if I can lower bound C, get a lower bound C on pi and Q, then I have an upper bound on pi Q inverse, and then I can use again the Portkey algorithm. Okay, this is just a side note because this is what the trick we are going to use in our example. Okay, so let's actually see an example, because this is all very abstract right now. So our example is going to be that of a Bayesian correlation estimation model. So think of observations y1 up to yn, which are multivariate observations. Given some correlation matrix R, they are assumed to be from some normal distribution, mean zero covariance matrix R. So each of these y's are multidimensional vectors, p-dimensional vectors, and R is a p by p correlation matrix. Now, this is our fundamental setup, and what we want to do is estimate R. R is our correlation matrix. We want to estimate R. There are frequentist paradigms or regular paradigms. You can use, your sample correlation matrix and so on. There's a common literature on Bayesian methods to do this correlation matrix estimation, which is what we will be looking at. So in a Bayesian model, what we're going to have to do now is we're going to have to put priors on R, or a prior distribution on R. Now, R is a correlation matrix, which means it's a very specialized matrix. So let SP plus be the set of P by P correlation matrices. Now, what I need to do is I need to put a prior on a correlation matrix. This is where I'm dealing with a prior on a parameter that lives in a very restricted space. Okay. So in this paper by Lighty et al. In 2009, the priors they set are the following. If this looks a little daunting, let's just look at it and hopefully would be okay. What they say is that let's assume so in this block over here, what they're assuming is all elements Rij of capital R of the correlation matrix are assumed to have independent normal distribution with mean mu and variance sigma squared. Okay, so take your correlation matrix and assume all of the entries are distributed mean mu and normal normal mean mu and variance sigma squared. However, the final matrix that you get with this prior assumption should still be a correlation matrix, which means that if I take the product of those independent placements, I then also need to restrict with the indicator that the final matrix R should be in SP plus. Right? So this is my prior distribution. Now, this product needs to actually integrate to 1, which means it actually needs to be a density. And so if I integrate this whole thing, whatever that turns out to be is I denote by L inverse mu comma sigma square, and I multiply that here, now ensuring that this F is a proper, well-defined prior for a correlation matrix. Okay. Now further, because choices of mu and sigma square can bias, if we choose them ourselves, can bias our analysis. So we want it to be a fully Bayesian setup, which means mu is given a prior, a hyper prior of normal 0 tau squared, and sigma square is given a hyper prior inverse gamma A0 B0. Okay. Once this is done, Lighty et al. Say that the interest is in the posterior distribution of R, the actual correlation matrix, and mu and sigma squared, the mean value in the correlation matrix prior, and the variance in the correlation matrix prior. Now you can see where the issue is going to come in. Hopefully, it is the fact that the prior distribution contains an unknown integral that is a function of the other two parameters, mu and sigma squared. Okay? So now it's the prior distribution that is in the form of an integral, which means the posterior distribution is also in the form of an integral. Okay, and it's actually in the form of an integral in the denominator. Okay, but the following MCMC steps can be implemented. So what you can do is you can do something called metropolis within Gibbs or component-wise algorithms, where they say that the components of Rij can be updated one at a time, where Frij given every other element of R and mu and sigma square is proportional to this density. It does not involve that annoying L integral. And so the Rijs, all of them can be updated without any issue. But then we also have to get samples for mu and sigma square. We also have to get those within this setup. And that becomes challenging. So F mu given R and sigma square, the full conditional distribution of mu and sigma square, both of them involve this L, which remember is 1 divided by an integral. Okay? So I can't evaluate F mu given the other variables. I can't evaluate sigma square given the other variables. So now running these metropolis Hastings steps for these updates for mu and sigma square is not possible using our usual tools. And so what the original paper Lighty et al. Ended up doing, they ended up using an approximation to this posterior distribution, and then used an approximation there to finally obtain some approximate solution. Yeah, go ahead, Ananda.
So the L is just a normalization factor, is it not?
L is a normalization factor that is a function of both mu and sigma square, which are parameters I want to estimate as well. Right?
Okay, so, but since we're just using that proportionality, can we not just like
but the parameters are so okay. If we had chosen mu, if Lighty et al. Had chosen mu and sigma square to be fixed numbers, then mu and sigma square cancel out because they're fixed numbers, right? Yeah. But the model that's assumed, because typically in a full Bayesian setup, you don't want to fix them, you want to give priors to them. So now that you've given priors to them, our whole parameter space is the full matrix R and mu and sigma square. So now our joint posterior distribution is a function of R, mu, and sigma squared. Right? And as a function of mu and sigma squared, there is an integral over here that cannot be evaluated, which depends on mu and sigma squared.
Okay, so just because we're using proportionality, we cannot remove this normalization thing because it depends on mu and sigma squared.
Exactly. That's exactly.
And how do I calculate this indicator here?
We don't calculate the integral. The integrator. It's in the sense that the density is saying that this density is valid for a multivariate R p by p correlation matrix if the final R matrix is a positive definite matrix that is a correlation matrix. Right. So if we're evaluating, so let's say we're evaluating this. So let's say I'm given a valid correlation or any matrix, and I want to see what is the density value of Fr for this R matrix. Then I will put in all the elements Ij, my mu and sigma square, calculate all of this, and then also check whether it is a valid correlation matrix or not, following the rules of correlation matrix. If it is, then I will get a density value. If it is not, then I will get 0.
Okay, okay.
right? So basically, R belonging to S plus P is the support of the distribution, right? The support of a correlation matrix is such that the actual matrix should be a correlation matrix, right?
Yes, yes.
Yeah. So it's very similar to saying that for a gamma distribution, the support is the on the positive line, right? So I have
Okay,
to
so we are just trying to make all those terms zero for those which are not correlation matrices.
yeah, exactly. So this particular trier density or this particular density says that the density value of a matrix is zero if it is not a correlation matrix. So
Yes.
that means in the prior it is saying correlation matrices that are not valid correlation matrices get zero mass in the prior, which is correct because I want R to be a correlation matrix.
Yeah. Okay, 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 it's clear.
Okay. So what the solution that the original authors presented was like a double approximation to actually get some sort of a solution. And so what we can do now is actually we can implement exact inference and exact MCMC because of the port key or flipped port key method. So I'm just going to focus on the mu update. If I look at f of mu given r and sigma squared, that is proportional to this over here. Recall L inverse is this integral over here. But now this integral, I can actually bound and estimate L inverse very simply. And I'll show you how. If I can bound this whole thing and I can evaluate or I can estimate L inverse using that Monte Carlo strategy, then I can implement my flipped port key Barker's algorithm. So what I'll do is I will be able to lower bound this whole thing. Now all of this first term are all known. So I just need to lower bound L, which means what I need to do is I need to upper bound L inverse. But L inverse mu comma sigma square can be upper bounded because this integral can be upper bounded because R is a correlation matrix. This integral can be upper bounded by integrals from -1 to 1 because the correlation matrix has all entries between -1 to 1. And using that trick, we get that L inverse mu and sigma squared are upper bounded by the Gaussian CDF of sigma squared, sigma inverse 1 minus mu minus sigma, Gaussian CDF sigma inverse -1 minus mu. Okay. So using just the fact that this integrand can be upper bounded, I can upper bound L inverse by some C tilde mu. Okay. And then that gives me a lower bound for F completely because I've been able to upper bound L inverse. Now, once I've been able to upper bound this and the fact that this integral I can easily estimate using Monte Carlo, I can then do my Bernoulli P star updates, and I can implement my port key algorithm, which is exactly what I'm going to do. And I did. What we did is we ran this for the closing. We had the data itself, the Y1 up to YNs, are data collected from 4 major European stocks between 91 and 98. So there are 4 European stocks. We tracked, there's data available for that. So the track data available for those 7-8 years. And then for all those 4, so we want to get a correlation matrix of how these 4 European stocks are correlated with each other. So what I did was I ran the Bernoulli, the Barker's algorithm, which represents beta equals 1, and the port key Barker's algorithm for beta equals 0.9 for a length of 100,000. Okay, so I start my Markov chain for this posterior distribution, and I run my Barker's Markov chain for 100,000, and I run my port key Markov chain for 100,000 with beta equals 0.90. And for every single step of this 100,000 steps, for every step, there needs to be a Bernoulli factory algorithm. And all of those Bernoulli factory algorithms require some looping, right? It will loop for a certain amount of time. And I track how many loops did every acceptance take or rejection take, and how many loops did every step take. So for each of those time points, for each of the lengths of the Markov chain, that's on the x-axis. And on the y-axis is the log of the number of loops it took to update mu. just mu. There's a separate loop I'm doing for sigma square, but this is just mu. Now this is on log scale. So now you can see that there are some acceptances that are taking roughly e to the power 12 steps just to get the Markov chain to do one step. So e to the power 12 is the number of loops for original Barker's algorithm in order to actually get an answer of whether to accept or reject. On the other hand, the Portkey Barker's has a probabilistic cap for around e to the power 4, e to the power 5. And that is because I'm using beta equals 0.90, which means roughly 1 out of every 10 are going to be rejections. Right? And so it becomes really, really much faster in the sense of the number of loops I will expect the Bernoulli factory to take. All of this is useless if my Markov chain becomes considerably worse, right? So if I get answers very quickly, it's useless if the quality of the answers are not good. So we have to look at the quality of the answers as well. And I can do that using the ACF plot or the autocorrelation function plot, which tells me what is the correlation in the Markov chain after certain lag. So the solid line is beta equals 1, and the dotted line is beta equals 0.9. And we see that there's only a very little loss for mu for the dotted line for the beta equals 0.90. It's very little in the beginning. And there's almost close to no significant loss, and there might be some gain in the for sigma squared. So what I'm saying is that they're almost effectively equal in the statistical performance, but the computation performance is far better. I can actually summarize this. So we average results from 10 replications of length 10,000. Am I running over time?
Yeah, a bit.
A bit. Okay, I'll wrap up. I'll skip 2 slides. Sorry about that. Thank you. Okay. So what the ESS I don't want to get into, but what's most interesting to see is if I just look at the 10 replications of length 10,000 each, the average max loops for mu in each of those 10 replications is about 2 million. I think this is 2 million. I think. Versus for beta equals 0.9 is 34. And ESS, which is effective sample size, basically says effectively the quality of the samples is roughly the same. These numbers are expected to be, if they're the same, that means they're effectively the same. But the key here is I could actually only do 10 replications as beta equals 1, that original Barkers would get stuck in very large loops and I'd be staring at a computer. And the port key would happen very quickly, but I couldn't actually do proper comparisons because the original Barkers would get stuck in these long, long loops. And when I tried to properly tune the proposal, so there's a whole literature on how to tune proposals, and there's literature that says that the Barker's acceptance function should be roughly 15.8%. So I should aim to accept roughly 16% of my proposed samples. If I tried to tune this, choose my proposal so that this happened, beta equals 0.90 gave me 10,000 samples in 40 seconds with reasonably good performance. And beta equals 1, which is usual Barker's, did not even do 1,000 samples in 24 hours, at which point I cut the simulation because I did not have time to waste. Because I'd have no idea how long it will take. It's an infinite blinking cursor. I have no idea how long it's going to take. But it did not complete 1,000 observations in 24 hours.
So I have a question.
Oh, yeah.
So can you go back one slide? So what does it mean by this, like the Barker's optimal acceptance rate is 15%? Doesn't it depend on theta and theta star?
So see, acceptance rate meaning so theta and theta star are fixed quantities for which the Bernoulli factory is running. But the actual Markov chain is actually proposing new theta stars every time, right? And changing the current state of the Markov chain. So there is whole literature out there as to if you have a Markov chain, if you have a proposal distribution, how should you tune the proposal distribution? Tune as in, you can choose proposal distribution with high variance, low variance, and so on. How should you tune the reach of the proposal distribution given in a particular problem. And the literature for Barker's acceptance function says that you should tune so that you have roughly 16% acceptances. Because you don't want to accept too often, because if you accept too often, it is going to force you to make small steps. Then only you will accept too often. If you reject too often, then you're not moving, which is also not good.
So too often is bad. How is too often bad?
So ideally, too often is great. But the problem is, if for a given proposal, if you say I want 100% acceptances, and then it's going to force you to make very small jumps. Wherever you are, it's going to force you to go very close to the current step. Only then it will say that I will accept every time. If you're just going to go like an inch, very quick, very close step.
Okay, so
And
the
that is not
converse
good,
effect
because you,
is that what you're saying?
exactly. So then you'll have high correlation in the Markov chain, because every subsequent step is very dependent on the previous steps,
Okay.
right? So there's literature, a lot of literature on what are optimal acceptances. The optimal acceptance for Barker's is known to be about 16%. And if we try to do that, then we stare at a blinking cursor, because we start doing large jumps, which it doesn't want to do. The Barker's two-coin algorithm just stops then.
Okay, so can we go back like 2 more slides of that graph? Oh, one more. No,
This
no,
one?
one more. So here for beta is equal to 0.9, so it's most of it stops around 3. That would be like 8. After 8 iteration, it stops.
E to the power 3, yeah, which is about 8, yeah.
Oh, no. Oh, I was thinking about 2 to the 3. Sorry.
E to the power 3 is about 3 to the power 3, which is 20, what is it, 27 maybe? Yeah. It's about 20, about 30.
So all of it stops in about 30.
Yeah, probabilistically, obviously, the probability that in 30 draws, a Bernoulli 0.90 does not give any zero, sorry, is very, very small. So it's not going to happen. Right?
And the black ones for beta is equal to 1. Some of the points are really high, like
Yeah.
2 to the
This
12,
is the
but almost all of them stops at around the same time, right?
That's right. So some of them are really high, but this is not for a properly tuned one. If I tune it, if I try and reach out to really get a good quality Markov chain, then I cannot even make this plot, because it is stuck in an almost numerically infinite loop. I don't even know, because it goes to e to the power 500, and I don't have resources to wait for e to the power 500 as an example, right? For one acceptance. So this is the best we could do. I could run this, and in this I show that I've not done any tuning. It's a bad Markov chain in the sense that I haven't been able to propose very well. But even then, it's doing e to the power 12.
So that is bad.
Yeah, yeah. So the original two-coin algorithm, this is the problem that it would always get stuck in. And so the port key correction sort of helps us do that without much effect on the actual statistical performance.
It's all almost similar.
Almost similar, yeah.
And so you chose the normal and inverse Gaussian distribution.
The Lighty et al. Paper. So we kept exactly their model. We didn't play around with their model.
Okay, so like how much effect like does the priors have?
So that's a modeling debate, and that's a modeling choice, and people might have. So I don't want to say that we don't want to worry too much about it. As an MCMC person, you give me the model, I'll give you the computation, right? So those are modeling choices, and they have, in the paper they talk about all the reasons to go in those choices. Most likely, these are convenient choices to make for them.
Okay, thank you.
Yeah, you're welcome. Yeah, I apologize. I'm going over time.
Sorry, one quick question. So the graph that you just showed is still like an empirical proof on a particular model, but theoretical bound exists regardless of the model.
Yeah, so the theoretical bounds of the variances are certainly exist. So this is the proof that we have in the paper. Yeah, this one. So this particular statement over here says Not much, because all it says is that the variance under Barker's is less than equal to essentially variance under Portkey, which we know. But the other one, which has an assumption that as long as none of the p theta stars and p theta are zero, essentially, we have a bound on the opposite direction that this is the worst we will do. So it's not infinitely worse.
Okay. But like given you're choosing beta to be very close, gamma depends on.
So gamma is coming from the problem statement, right? So if any of the p theta or p theta stars are very, very like this zero, then it becomes really challenging.
Achha,
But that typically is not going to happen.
Okay. Fine.
Okay, I have one slide. I'm sorry, Rucha, I apologize. I have one slide, if I can get to it.
Yeah, no problem.
It's taking time. There we go. Okay, so the work itself, if you want to read more about it, I think this is probably one of the more easier paper to read. The proofs are very simple, and I think we've tried to write it in a reasonably palatable way for for an audience not familiar with MCMC too much. And so this is in Biometrica 2022 last year. Just to summarize the advantages and disadvantages, the advantages are particularly that there's a lot of, going back to what Anada had proposed, there's a lot of approximate methods out there that sort of do approximations in such challenging problems. And what the nice thing about this, even two-point algorithm and Portkey both, is that these are exact methods, and they come with all the guarantees that MCMC literature gives us. And then further for the Portkey is that the Markovian dynamics are very mildly altered for beta close to 1, which is the beta we typically choose. Which means that a lot of what we know about Markov chains and Barker's and Metropolis Hastings can sort of carry through to these Portkey algorithms as well, at least on a wishy-washy level. Again, I said these are exact MCMC algorithms with no approximations. And further, the Portkey Barker's is significantly robust. And the point it's very difficult to make for this paper is that in order to tune the original Barker's or two-coin algorithm, it requires staring at a blank screen so often. And as a person who's riddled with insecurities, if I'm staring at a blinking cursor, not knowing when it will stop, drives me mad. Versus Portkey, which will tell you it's stopped, Markov chain is good, Markov chain is bad. Right? So at least it gives you an immediate answer within flashes of seconds, rather than what feels like days. That really is the key to why the Portkey can be very effective. The disadvantages certainly are that there is loss of statistical efficiency from MH to Barker's and then Barker's to Portkey. So statistically speaking, we will not ever be doing better, which is a shame. And then obviously finding the bounds is necessary. And this is really something we want to work on more, is what are the problem spaces where these bounds, either lower or upper, can easily be found. Not all problems are easily amenable to such bounds. So that's really one of the spaces we really want to see if we can come up with more general bounds rather than problem specific bounds. Okay, I apologize again for going over time. I appreciate the questions though. So I'll take more if there is time. Thank you.
There is one question more.
Okay.
So the way you justified it that like if we take smaller steps, we'll be stuck to a particular area, right? Does 0.9 is a good trade-off in that? Is that you are saying beta equal to 0.9 is a good trade-off that we go further enough?
Oh, so beta is completely disconnected to the acceptance rate.
Okay.
So let me go to the very first slide. These transitions are very slow on this document for some reason. But let me just explain this part over here. If I can reach there. Okay. So if I go to this step over here, you see this Q is what we're talking about when we're talking about tuning the acceptances. So for example, let's say I want to sample from the Lighty et al. Model. Typically the Q that is chosen is, let's say, a Gaussian distribution centered where I am. So wherever I am, I'm going to put a Gaussian with some variance. Okay, and then that's going to propose a value close to where I am, right? And that value I'm going to accept or reject based on the alpha acceptance probability. So Gaussian kernels are very common to be commonly employed. So these are random walk metropolises, random walk proposals. But now the variance of this Gaussian proposal is something I can choose. I can choose the variance to be much large, I can choose it to be very thin. If I choose the variance to be very, very thin, then I am choosing values close to where I am. And if the value where I am was a good value to accept, then a value close to where I am is likely also a good value to accept. And so I will get high acceptances. That acceptances has nothing to do with, or well, has not as much to do with the beta, because that beta is within the Bernoulli factory, which is a separate problem. Okay? So
I see.
for the quality of the Markov chain, to make sure I'm proposing farther enough values and assessing and moving nicely in my space, I want to be able to tune it well so that the Q is chosen so that it can go far away. The challenge is when I try to make it go far away, it often goes in areas of a high probability where it would want to, low probability, where it would want to reject to begin with. But the two-coin algorithm in areas of low probability takes so long to decide to reject or accept that now I'm staring at a blinking cursor. Right? That is where beta equals 0.9 is helpful. That if I've chosen a value too far away, instead of looking at a blinking cursor, it just goes to the port key and just says, just reject. Okay, don't worry about it, just reject. Go and get a new proposal.
But that beta tells that even after so many rejections, you still have to find a new one, right?
Yes, correct. That certainly is true. Yeah.
Okay. Thank you. Yeah.
You're welcome.
Anyone else has any questions? Am I audible?
Yes, to
I
me,
have
yes.
some network issues, but yeah, okay. Thank you, Dr. Watts, for engaging presentation. I'm assuming it was really insightful for many of us. Thank you so much.
Thank you so much for having me. I appreciate it.
Yeah. Another says thank you to you.
No, interesting work. I hope somehow we can find an ML where we can push this. Yeah.
There are some places where I think it is applicable, but I haven't explored them very actively. But yeah, if some ideas come in, I'd be happy to talk about that.
Yeah, sure. Thank you again. Yeah.
Okay. Thank you.
Yeah.
Thank you.
So,
Have a good evening, everyone.
yeah, you too. Thank you, everybody, for joining in here. I hope to see all of you for the next one. Okay, bye bye. Thank you.